Okay, so today we're going to talk about how we can use molality to look at freezing point depression and boiling point elevation. I know I tell you guys that a lot of topics are my favorites. This is truly one of my favorite topics. I really like all the stuff that we learn at the end of the year, but I think that this is really cool. And so it's referred to as what's called a colligative property. A colligative property is a solution property that depends on the number of solute particles present. For example, the freezing point and the boiling point. So when we add a solute, okay, so something that we dissolve, when we add a solute into a solvent, very often, 95% of the time, we're talking about water, the freezing point depresses, meaning the freezing point gets lower, or the boiling point elevates. So for example, we can take sodium chloride and we can put it on the roads in the winter because we don't want the roads to freeze. The sodium chloride, the solute, the salt, causes the ice to form at a lower temperature. So rather than freezing at 0 degrees Celsius, now it freezes at, I don't know, -4 or 5 degrees Celsius, depending on how much is there. It also elevates the boiling point by not quite as much, but it does elevate it. So you could, if you're cooking pasta, some people put salt in the pasta water to raise the boiling point so that it cooks at a slightly higher temperature. It does raise the temperature slightly, but it's very slight. Typically, when you put salt into boiling water, you're doing it as a seasoning and less as a boiling point elevation. But that is a side benefit. It does raise the boiling point. So there are constants. We call it K, and we put a little BP next to it so that we know one's for the boiling point, and the one for water is 0.515 degrees Celsius kilograms per mole. That will be given to you. That's not something that you have to memorize. So it's telling us that 1 mole of a solute particle will raise the boiling point of 1 kilogram of water by 0.515 degrees Celsius. So we're looking at half a degree, not a whole lot. So if we have sugar water, which doesn't dissociate and doesn't break apart, if we have a 1 molal solution, we do 1 for the 1 mole times that degrees Celsius, and our new boiling point of 1 mole of sugar water, which is quite a bit of sugar, will raise it by half a degree. Now we said these colligative properties depend on the number of ions present. So sugar, even though we have C6H12O6, doesn't dissociate. It doesn't break apart. It's a covalent compound. If we have something like sodium chloride in water, sodium chloride is an ionic compound, and sodium chloride is going to dissociate. So if it's going to dissociate, it's going to break apart, and it's going to break apart into Na plus and Cl minus. So here I have to take into account how many particles I have, so it's 2. So a 1 molal solution of salt water, NaCl, will now make the temperature 101.03 because I'm multiplying this 1 times this number, and I always have to go back in and add in the boiling point. So I'm adding back in the 100 degrees because water will always boil at 100 degrees. I'm looking to calculate how much more. And if I have a 1 molal solution of calcium chloride, what do you predict this number will be here for calcium chloride? We're going to break into Ca plus 2, and we're not going to make a Hunkelbrief because it's aqueous. We're going to make 2 Cl minus 1s. So we have 3. So calcium chloride has the greatest effect. The same concentration of solution will make the solution 101.545 degrees Celsius in terms of boiling point. So we need to take into account how these things split up. That's why they're referred to as colligative properties, because they are based on the number of ions present. And I'll just put that definition up back again real quick. Depends on the number of solute particles that are present. And so that's where that comes into play. So to actually do some calculations, we have a freezing point constant. And it's telling us the same thing, that 1 mole of solute particles will lower the freezing point of 1 kilogram of water by 1.853. And so 1 mole solution of sugar water, we're going to go through this again, will cause the freezing point of water, which in Celsius is 0 degrees Celsius. We need to subtract that amount. And so sugar water will freeze at, close to -2 degrees Celsius. A 1 mole solution of salt water, again, will have twice the effect. So 2 times that amount. And so now water will freeze at -3.7. It's almost -4 degrees. And a 1 mole solution of calcium chloride water will freeze at 3 times that amount, or close to -6 degrees Celsius. And this is what's used a lot on the roads. It's more expensive than sodium chloride, but it gives us those couple extra degrees to keep our roads safe and from being icy. And so you'll see that a lot of times we refer to as rock salt. It has a calcium chloride component in it to help reduce that temperature by almost 5.5 degrees. So our equation looks like this. The change in temperature, because it doesn't tell us what the final temperature is, it tells us how much lower or how much higher the temperature is going to be, is equal to I, and I is your number of ions. M is your molality, and K is the constant. And again, the constants will always be provided for you. So our constant, our freezing point, and this refers to water in this case. 95 to 98% of your problems will involve water. So here's how we'll solve it. If 26.4 grams of nickel 2 bromide are dissolved in 224 grams of water, what will be the new freezing point and boiling point of the resulting solution? Well, I have to solve for my molality first, and so I'm going to do that up top because I need that for both of them. I have grams. So I'm going to take my 26.4 grams nickel 2 bromide is NiBr2. I'm going to go ahead and convert it to moles. So 1 mole of NiBr2 to 18.49 grams of NiBr2 equals 0.121 moles of NiBr2. I need to find my molality. So molality is equal to moles per kilogram. My moles is 0.121 moles. And my kilograms is 224 grams of water, but I need to make that 0.224 kilograms. And I solve that, and I have 0.540 moles per kilogram, or molal. I can just use that lowercase m, and that capital versus lowercase m is going to be really important. So if I'm looking for the freezing point, delta T freezing point is equal to I, my number of ions. NiBr2 looks a lot to me like CaCl2. How many ions is that going to break into? Well, of course it's going to break into 3. My molality I already solved for. It's 0.540 m, and my temperature is 1.8, my constant, 53 degrees Celsius kilogram per mole. So I solve delta T freezing point, and I calculate it by typing it all in. So 3 times 0.540 times 1.853 gives me 3.00 degrees Celsius. So it's freezing point depression. Does the water freeze at 3 degrees Celsius? No. There's always one more step that just shows up. We have to take whatever our freezing point of our substance is. So we have 0 degrees Celsius, and we're going to subtract the 3 degrees Celsius. So my freezing point, my temperature, my freezing point, not the change in it, is negative 3.00 degrees Celsius. Let's pick a new color here so it doesn't get confusing. I'm going to do the same thing for boiling point. Delta T, boiling point. It's still 3 ions. It's still 0.540 molal, but my constant is now 0.515 degrees Celsius kilograms per mole. I'm going to go ahead and solve for my boiling points. So 3 times 0.540 times 0.515 gives me 0.834 degrees Celsius. That is not my new boiling point. The boiling point is 100 degrees Celsius, so it's an elevation. I need to add that. In this case, this is one of the few cases where we are actually going to break the rules of significant figures, because otherwise it would be negligible. So I'm okay with you going ahead and adding on your 3 significant figures, even though I know it is sort of insignificant. We're considering the 100 to be an exact number, so we need to add that on. And let's try one more. If 25 grams of calcium chloride are dissolved in 500 grams of water, what will be the new boiling point and freezing point of the resulting solution? The constants are the same as they were before. So I'm going to ask that you go ahead and pause the video, and I do really hope that you guys do this. If you want to do well, this is the thing to do, and self-check. Pause the video, solve the problem, and check it. I know you can just copy it, and I know you might make mistakes, but the mistakes will lead you to not make further mistakes. Okay, let's take a look at it. I took my 25 grams of calcium chloride, I converted it to moles. I took my moles and I solved for my molality by using 500 grams of water, making that kilograms, and getting 0.45 molal. I solved for the freezing point. I know it's a boiling point and then freezing point. I kept it consistent with the last page. So I did my freezing point, my change in temperature of my freezing point, 3, because that CaCl2 is going to break into Ca and 2 Cls, my molality, and then my constant, which should be given to you. I solve, I get 2.50, but I know that it lowers the freezing point, so it's 0 minus 2.5, and I get negative 2.5. To look at my boiling point, the temperature of my boiling point, same 3, same 0.45, my new constant's 0.515. I get 0.695. I know it raises my boiling point, so I add it and get that. And again, don't worry about the significant figures in this one case where we're adding it to 100, because otherwise our answer would be inconsequential, and I need to be consequential. And so that's sort of accepted, since 100 is the actual boiling point.